One more quick fact before moving on. I said the theorem stays true for the null recurrent case. So this means that if we take the symmetric random walk on the integers that we said, was in fact null recurrent, you go up probability 1/2, down probability 1/2, then this means this also doesn't have an invariant distribution. And so that's kind of interesting. And even though it's a reasonably nice process, it doesn't have invariant distribution because it's just not nice enough. You need to be positive recurrent to have an invariant distribution. So this interpretation of the invariant distribution represents how much you want to come back. It means that null recurrent is not good enough. You really need to be positive recurrent for it to want to come and visit that state. All right, good. The last thing we're going to do in the videos is talking about the proper aspects of the limiting behavior, how equilibrium comes out in the limit. And this is what you could call the main theorem of the module. And it's to some extent a combination of quite a lot of things we've done. So pretty big theorem, pretty great theorem, really interesting. So we have our Markov chain, and we're going to assume a bunch of things. We assume that it's irreducible, aperiodic, that's new, haven't mentioned aperiodicity in a while, and that it has a stationary distribution pi. Then the distribution of the state of the Markov chain at time n converges to pi as n tends to infinity. So pi n converges to pi. I will in fact write the theorem down, but we'll do the proof on the slides because the proof is definitely on the intense side with quite a few things to it. So this is theorem 20. So as I often do, I'm going to paraphrase it a little bit. So in fact, let's make it as a list. So assume that the chain, so the chain xn, is irreducible. Okay. I'll remind you, irreducible means there's only one class. It means I can go anywhere. In principle, I can go anywhere, from anywhere, and come back as well. Is aperiodic. So that's, this is the first time this shows up really in a theorem. Aperiodic means that the joint period of all the states is 1, and it means that you can come back in various amounts of times, which overall are co-prime. So maybe I can come back to my starting point in 5 and 11 steps. These two are co-prime, so it makes the period 1. And finally, has its stationary distribution pi. Then pi n, so that's the distribution of the chain at time n, converges as n tends to infinity to pi. This is a convergence of row vectors. So it really just means every component converges. So I'll write this, i.e. p of xn equals I converges to pi I when n tends to infinity for all I. The probability of being 3 converges to pi 3, and so on. So this is, the theorem that we observed in the first session, where I used R to compute the probability that Alex was at office A and B and C, and we ended up seeing that it did seem to converge to a vector, which was indeed an eigenvector of a matrix. Back then, we weren't using the actual transition matrix, but this transpose, so we had a right eigenvector, but with a proper setting, it's of course an invariant distribution, which is a left eigenvector for our things. Good. Go back to the slides. So we'll try and look at the proof. Oh, before that, yes, worth mentioning extra small detail. This holds true whatever the initial distribution is. So pi 0 can be anything. This is why it doesn't actually feature in the statement, because it's not particularly relevant. But you can start at 1, you can start at 2, you can start at 3. Things kind of mix up, and your convergent probability is the same. It's always pi. This works when you're reducible and aperiodic and have the stationary distribution. We will see, we'll see in the next session that we can more or less, if we remove these two, the theorem changes. Let's put it like that. All right. Let's go with the proof. So the proof uses a special argument. Like we're not actually going to start directly, compute pi I, and show that it converges. We could do that, and there is a theorem which does that in the world of algebra. And you can look it up. If you're curious about the link with algebra, I encourage you to look up a theorem which goes by this name. So Perron-Frobenius theorem. And it's essentially a linear algebra version of our thing. But we're going to give a proper probabilistic proof, which is much more fun, if I dare say so. We're going to use coupling. So what is coupling? I'm going to take two versions of my Markov chain. I have my xn. Okay, xn is the Markov chain. It starts with any probability distribution pi 0. I don't really care. And then I'm going to take a yn. And yn is a Markov chain with the same transition matrix P, but I'm going to give it initial distribution, my invariant stationary distribution pi. And I run both of them independently. So, this means in particular that probability that xn equals I is pi in, probability that yn equals I is just pi I. This one doesn't depend on n. And so I want to show that this probability, will become close to that probability. And the way we're going to do it is we're going to see that xn at some point will become kind of like yn in some way. So specifically, what we're really interested in is the possibility that the two chains meet up. So, they're both chains on a finite state. Actually, no, it's not necessarily a finite state space. So there are two chains on a state space. They might at some point meet up, and so we're looking at any possible m such that xm equals ym. So what's really interesting is that, if this happens, then by the Markov property, first off, what happened before, we don't really care. Obviously, it won't affect the probabilities of what happens afterwards. But what happens afterwards, the probabilities will become the same. So after the first moment where they meet, the two chains xn and yn actually will have the same distribution. That's really interesting, because what this means, if you think about it, probability that xn equals I minus probability that yn equals I, so the difference between the two, is going to be less than the probability that the two chains haven't met before time n. So the full explanation is in the notes, but this is what happens, right? If they've already met, then the probability will be the same. Hence, the difference between the probabilities should be less than the probability that they don't meet before time n. So what the proof is actually going to focus on now is this bit. We're going to just try and show that this probability, the probability that they don't meet before time n, tends to 0 as n tends to infinity. So we see that it's decreasing, but let's see that it actually tends to 0. So yeah, this is what I just said. And a thing with probability, again, there's kind of a bit of theory that we don't quite know, is that it's the same thing as showing that the probability that they never meet is equal to 0. That's going to be our objective. show that the probability that they never meet is 0, the same thing as saying that the probability that they do eventually meet is equal to 1. To do that, I'm gonna put both x and y together in a big Markov chain that I call bivariate, because it kind of has two variables, x and y. And that makes a Markov chain on the bigger state space. This makes a Markov chain on S times S Cartesian product. And that's still fine. This is still a state space. And we have a funny Markov chain with a funny transition matrix, which we shouldn't really think of as a matrix because it's a bit too big, but that's fine. And what I'm going to do, so this new bigger Markov chain, we're going to show that it's irreducible and recurrent. And if we have both irreducible and recurrent, that's a thing we kind of know. It's going to visit everyone. If you're irreducible and recurrent, you're going to keep coming back to your starting point, and from your starting point, you're going to eventually visit anyone. So in particular, if it visits everything, it's going to visit a state like II, 1, 1, 2, 2, 11, 11, one of these. And if it meets a state like that, it means that x and y meet, which means we've finished. Okay, so I'll say this again because this is kind of neat. If we show that this new chain is irreducible and recurrent, it's going to visit everyone. In particular, it's going to visit states which are like 1, 1. And if it visits 1, 1, then it means we found a time at which x equals 1 and y equals 1, which means that they've met. That was what we wanted to do. We wanted to show that they meet with probability 1. Good. So how am I going to do that? Well, first off, this new chain has a funky transition matrix. We're not going to write it as a matrix because it's not so convenient. Instead, I'll just notice that the probability of transitioning from I1, I2 to J1, J2, so I for x, sorry, I1 for x and J1 for the next step in x, then I2 for the current state in y, and J2 to the next step in y. Since x and y move independently, we're going to get that is just the product of each transition. X goes from I1 to J1, so Pi1, J1. Y goes from I2 to J2, so Pi2, J2. Quite natural. And knowing that, we can actually do most of what we want. So let's first look at the fact that we're irreducible. So since the original Markov chain is irreducible and aperiodic, Theorem 6 tells us something interesting. So Theorem 6, or a variant of it, Theorem 6 was telling us that for all n large enough, PIIn is positive, so probability of returning is positive. Since we're reducible, I can also go from I to j, and so Pij in n steps is positive. Not for every n, but like for all n bigger than 59. That's going to happen. That only works because you're aperiodic. If we were periodic, we'd have to miss out on some n's, and that would be a problem. So now, I'm going to take I1, I2, and J1, J2, and because of what we just said, we can say that Pi1, J1, 42 is positive, and Pi2, J2 also in 42 steps is positive. So if they're both positive, the product is positive, and that means that this new bivariate Markov chain can transition from I1, I2 towards J1, J2 in 42 steps. When I say 42, I just mean, in principle, there exists a value where if you're large enough, it works. Good. Because, that literally means we're reducible. That's what it means. Hence, bivariate Markov chain is reducible. That was one bit. Next bit is that we're going to show that it's aperiodic. So yeah, I've mentioned this in the slide. Aperiodicity is crucial to this argument. Otherwise, we would be missing some values of n, and we would get different values for I1, J1 and I2, J2, and so this wouldn't work. We'll see more about this when we actually cover periodic chains. Proof that the bivariate chain has a stationary distribution, that's easy. You actually just need to check it yourself. I'm giving you the value. It's just pi for x and also pi for y. That makes sense. think that makes sense because, you know, each of them has its own invariant distribution and they both evolve quite independently. So check this as an exercise if you like. So what we've done, okay, so we have now an irreducible Markov chain on the bivariate state space, but that's fine. It has a stationary distribution. So what have we done? If you remember proposition 19, we said that if you're transient, you can't have an invariant distribution. So if we have an invariant distribution, we have to be recurrent. If we're recurrent, it means that we meet everyone. If we meet everyone, that's what we were trying to do. We're done. Proof is actually finished based on things we've said earlier. So that's good. That's great. We've shown theorem 20. That may have looked a bit intimidating, but this coupling proof is very neat and very much an unusual probabilistic argument. Let's cover one final thing to finish. There's a useful corollary, which is basically uniqueness. If you're irreducible and aperiodic, the stationary distribution, if it exists, it's going to be unique. Why is that? Because, you know, limits are unique. We said that pi n converges to pi. It can't converge to anything else. So there's only one stationary distribution. So remember, you know, I was saying earlier that we were going to learn when the stationary distribution is unique. Here is the main corollary we have, and the result we have for this. If you're irreducible and aperiodic, then it has to be unique when it exists. Actually, though, let's go one bit further. Turns out this is true without the aperiodicity assumption. So the proof we did relies on aperiodicity strongly because it happened in the middle of the big convergence. But actually, and you can take this is fine. Uniqueness of your invariant distribution, you only need basically to say that you're irreducible. So you can do that, you can assume that. I'm not going to actually give the proof, but that's okay. All right, and you know what? I think we're done. Yeah, so we're done with the videos. You can now, you know, you can actually start working if you want on some exercises in chapter 4. Because we know what invariant distributions are and we know how to find convergence. I will definitely come back to this and cover some more of it in the next lectures. But yeah, we have a bit. You can also do the bit of homework, which I haven't assigned yet, but I will in a bit. So go ahead and do that. I hope this was all okay and that you didn't find this too different from the lectures. And I'll see you all after Easter break. So have a good time. Relax if you can. Work if you can as well, because it's going to be useful. But so try and find the balance between both. See you then. Bye.